I can't do this. Our last project was so terrible. They said we were so boring. I just got to jump. What was our PowerPoint for? No, Sal, don't. We're gonna make it up on this video. I promise. Yeah. Oh yeah! Starring Tyler Sellner. Die, zombies! Mom! Where are my hot pockets? Can't you get it yourself? No! I'm busy fighting off a zombie apocalypse! Starring Ben Jette.
Oh boy. Oh, those quesadillas. Oh. Oh, okay. Oh, jeez. I'm going there for a few hours.
Starring Reddington.
Alright, so I'm going to be doing the balloon and the candle experiment. This is just a normal balloon, just air in the balloon. And when I approach it to the flame is going to heat up the plastic of the balloon, burn a hole, and the balloon's going to pop. I won't even have to touch it to the flame. Alright, now this balloon has water in it, so when I approach it to the flame, the water is going to suck the heat off the flame, taking it away from the plastic of the balloon. Therefore, the balloon will not pop and the flame will actually be doused. And there it is.
Oh yeah.
Okay, so this next experiment is the unburnable money trick. I'm just going to show you that obviously a piece of money is going to burn when put in the fire because it's paper. Don't worry, there was parental supervision when that happened. So I'm just going to take a copper pipe and a dollar bill. I'm going to wrap the dollar bill around the copper pipe like so. And I'm going to hold the paper above the fire. And when I pull it away, it doesn't catch on fire like the paper did when the copper pipe wasn't there. There's just a scorch mark. This happens because the candle does heat up the paper, but the heat is quickly transferred to the pipe and sent away from the paper. Because of this, the paper cannot increase its temperature to the kindling temperature in order to catch on fire. As the heat from the candle enters the paper, the copper pipe quickly takes the heat away from the paper, and therefore it doesn't burn.
Okay.
Okay, so we got a frozen piece of pizza here. Can you confirm that?
Yeah, it's hard.
Alright, so we're going to place this pizza into a toaster oven and let it cook, and then at the end we're going to take it out and show you how it was cooked. Yeah, that's about it. And now we need to wait 15 to 18 minutes, so we'll be back when you start it.
Yep.
Halfway done.
What's Thermodyamics?
And as you can see, yeah. Get out of it. The pizza's done. It messed up a little bit, but you know, she's done.
It's hot. Ow.
Alright, now we're going to explain how heat moves within food. The most important thing to understand is that when you put food in an enclosed vessel like a grill, smoker, or an oven, the hot air, which has lots of vibrating molecules, transfers some of its energy to the exterior of the meat. The energy in the air excites the molecules on the surface of the meat, and then they transfer heat to the molecules inside it, and so on, slowly passing the energy toward the center of the meat like a wave of heat. It takes time because the meat is about 75% water, and water is a good insulator, especially when trapped inside muscle. The heat moves inward because physics dictates that the meat seeks equilibrium in an effort to make the temperature the same from edge to edge. So most of the meat is cooked by the meat, not by the air.
Elio's Pizza, available at all local supermarkets. Oh, it's already switching. It's already switching. Oh, yeah. For our next experiment, we have a glass bottle with water on the bottom and a balloon attached to the opening. And as we heat the bottom of the bottle, the water evaporates into gas, which fills up the balloon and causes it to inflate.
This experiment we're going to show what happens when you melt ice in tea. First we must discuss what cold means in physical terms. Obviously cold is a real sensory experience, but in physical terms cold is not a thing, it is simply an absence of heat. When you put an ice cube in a cup of tea, you're doing this to cool it, but in terms of physics this description is backwards. What actually happens is the heat flows from the tea to the ice, thus raising its temperature. The resulting temperature is somewhere between that of the ice cube and the tea, but one cannot obtain the value simply by averaging the two temperatures at the beginning of the transfer. For one thing, the volume of the water in the ice cube is presumably less than that of the water of the tea, not to mention the fact that different chemical properties may have some minor effect on the interaction. Most important, however, is the fact that tea did not simply merge with the ice. In transferring heat to the ice cube, the molecules in the tea expended some of their internal kinetic energy, thus losing further heat in the process. Alright, now we're going to do the magical can crusher experiment. I have a can of soda right here, but filled it with a little bit of water, and it's boiling, and a bucket of ice water. And I'm going to flip the can over into the ice, and hopefully the can will crush. Alright.
Yeah.
And there it is.
Brick Squad.
Now we're going to do a recap of the magical soda can experiment that we just did. When the water in the can starts to boil, the air is pushed out by steam from the boiling water. The airspace in the can is replaced by the steam. When the can is immersed in cold water, the steam turns back into water droplets, creating a vacuum inside of the can. The water pressure outside of the can starts to push against the walls. This causes the soda can to collapse.
The next experiment, I'm going to light this piece of paper on fire and throw it at the bottom of the glass bottle. When I put the egg, the hard-boiled egg on top, the egg should be sucked in, and abracadabra, that was pretty quick. When I drop the burning paper into the bottle, the paper burns until the oxygen is consumed, which increases the air pressure. The heated air pushes the egg out of the way, which is why the egg almost seems to kind of jump on top of the bottle. As the air cools, because the hot air is leaving the bottle, the egg settles down and seals the mouth of the bottle. So now there's less pressure on the inside, and there's a higher pressure on the outside of the bottle. So because of equilibrium, the higher pressure pushes right through the egg to get to the lower pressure.
Alright. Sunlight is a form of electromagnetic radiation. When electromagnetic radiation from the sun strikes the Earth's atmosphere, some of it is absorbed while the rest proceeds to Earth as heat. In the meantime, the electromagnetic radiation that wasn't absorbed by the atmosphere proceeds to the Earth's surface and heats it up. Some of this heat stays there while the rest is re-emitted. Upon reaching the atmosphere, part of it gets absorbed and part is passed through. Naturally, the ones that get absorbed add to the heat already there. Radiation from the sun ranges from infrared to ultraviolet rays, and when your skin absorbs the rays, that's what causes sunburns.
Who's got the next layer?
Equilibrium is the state in which two bodies in physical contact with each other have identical temperatures. Heat is the energy transferred between objects because of a difference in their temperatures. Conduction is the process by which energy is transferred as heat through a material between 2 points at different temperatures.
and delete that video. Okay.
Doesn't have suntan lotion. So we got whipped cream and ranch dressing.
We're not stressing.
Really?
I'm not. No one's putting it on.
Hey.
What am I actually gonna?
Alright, now we're doing the magical can crusher experiment. I have a soda can here filled with some water and it's starting to boil. And I have a bucket of ice water here and I'm going to flip this can over into the water and the can should be crushed. So let's do it. Oh, okay, let's do it again.
Blooper.